Last time, we explored how to replace one of these knobs on the Novation Circuit. And I also shared my experiences with the wonderful support that I got from Novation. However, while I was doing this, I discovered that what I believed to be encoders, these things, were actually potentiometers. And so this just left a bunch of questions with me. How can this be an endless potentiometer? Don't potentiometers resist current? So how does this translate into an endless rotary behavior? And how do I use this in my microcontroller sketches? I figured before we move on to another service video or any other project really, I thought, let's take some time and see if we can get a better understanding of what this potentiometer is and see how we can use her in our code. Yeah, if you want to follow along, we'll need a breadboard, an Arduino Nano, or Uno, or just about any of those will do, as long as you account for the pins. You want to make sure that they are analog input pins. Of course, we'll need one of these endless rotary potentiometers, the one that you are seeing right now on your screen. This is the datasheet for one of them. We'll need a 10K resistor or any kind of resistor just to make sure that we don't short the circuit. You'll need at least one multimeter. Yeah, we'll need some jumper wires. Of course, an IDE to load the code, and then a USB cable to, actually load the code onto the microcontroller. Okay, so before we get started with that first example, though, I want to show you a few things right here in the in the data sheet. First thing I want to show you, these are obviously the physical dimensions of the part itself. But here's the curious thing I want to show you. But a normal potentiometer symbol just looks like a squiggly line with a line down the middle, and that represents the shaft. So normal only has, potentiometer only has 3 pins. This one has 4. And the way that this is configured, that 4th pin is another wiper. What this leads me to think is that this really behaves like 2 potentiometers in one. So the shaft is actually controlling 2 resistive tracks, or maybe is one with 2 different pots at different angles. I'm not really sure. But just by looking at the datasheet here, we can see, so this graph right here represents the resistance taper. So on the on the horizontal axis here, we see the values represented as the shaft rotates, right, along that resistive track. So here's a position 0 degrees, and then 36 degrees, 72, all the way to 360 degrees, where it makes a full rotation. On this vertical axis, what we see is the percentage of the resistance as the wiper travels along that taper. As we go from 0 and then to half of the total travel, we see that it goes from 0 to 100% resistant, right? And then from half, or the 180 degree down to the end, 360 degree, we see that it returns from 100% resistant to 0% resistant. If we were just to keep going, because this is endless, then this would just look like a triangle wave. And of course, this could be problematic, because if we're trying to determine direction, well, we won't be able to, because if we say, oh, well, direction is going in this way, if the next, if the previous value is lower than the next value, well, that logic doesn't hold true once we get past that 180 degree point, right? So it becomes the opposite. And so that's why we use that second wave here. And as you can see, this second one is being offset. It's the exact same behavior, right? Except that instead of starting at the position is beforehand, right? So like if we look at this, when this is 0 here, 90 degrees prior, that's when this is 0 here. And so this is important, because when we do our calculations, we're going to have to take this into account. So I found this other post while I was researching for this. Let me bring it over here into view, because there's some interesting stuff in here, right? So here's something that the author, Jorn, figured out. So if you look at this, as you make one full cycle, there's actually, the pattern can easily be broken into 4 different parts, right? Let's call them quadrants, right? So in one scenario, A and B are both going up, right? In another scenario, A and B are both going down. And in the other two, we're just looking for when one is going down and one is going up. So one's going down and one is going up. With the only difference that this one right here, the first one, is going to happen on the upper range of the possible values. The one that happens later on is going to happen on the lower range of the possible values. More on this later, but for now, let's just see what this thing is doing, right? Let's just see how this is behaving by hooking up some multimeters and a power source and just taking some readings. Okay, for this first part of the experiment, this is what we're going to hook up. We have a power source connected on the positive rail, so 12 volts goes into 10K resistor. This resistor, and I chosen the value of 10K because the potentiometer I have is also 10K, and so I figured it would be easy for us to get some values out of this. So the resistor you see here is for protection only. This is so that when there is no resistance here, when it's fully open and we're sinking down all the current down the ground so that we don't cause a short, right? And so this is, any resistor value could really do. I chose 10 because it would simplify the math, right? Because if you think about it, this and this, if this is a 10K resistor or pot with a 10K resistor here, this is just a voltage divider, right? So if we have, this is its maximum possible resistance value here of 10K, and we're having a voltage drop between both of them. So from here to here, this is going to be 0. That means that if we have 12 volts up here, and so the middle point here is going to be 6 volts, which is the maximum value that we should be able to read from either one of these pins. When we do this, we should be getting something like readings of 0 volts, and then we move over 90 degrees, and that should give us 3 volts, and then we move another 90 degrees, and that will give us 6 volts, and then another 90 degrees, and we're down to 3 volts, and then when we're back again, we're back to that 0. First off, so this is the endless rotary potentiometer that we've been looking at. One thing you might notice that is different than most from all other potentiometers is that this has 4 pins instead of 3. Here's a little schematic of how this is wired internally. Now, I don't know if there is just one track and then the wipers are offset, or if there's 2 separate tracks. That's unclear from the data sheet. But what I do know per the data sheet is that the values are offset by 90 degrees. And so what does this mean? So basically what that means is that as we rotate this, if this is 12 o'clock, the 90 degrees is going to be 3 o'clock. So that means that if one of the wipers reads, say, 0 volts here, then the other one is going to read 0 volts when the position is on this side. So that's what we're trying to illustrate with this with this experiment here. So for this, what I have over here is a power supply that's going to be supplying me with 12 volts. That is connected right now to this plus here on the breadboard, and then the ground is on the minus. The other thing is I have a 10K resistor in series with the potentiometer. The other side of the resistive track here is pin 2. Pin 2 is connected to ground. And so what we have over here is 2 separate multimeters. The one on the left is connected to pin 1, and the one on the right is connected to pin 3. So let's go ahead and turn this on. Okay, And make sure when you're turning your multimeters, you want to set them to voltage, right? And it's going to be a DC. This one's a little different, but it's DC. Okay, so right off the bat, we can see this is at the 12 o'clock position. And sure enough, if we look at this, this is really close to 3 volts. In fact, because it's going to be really difficult for me to get an exact accurate reading in there, we're going to assume that that is 3 volts right there for the one on the left. I'm just going to write it down here. And this one here is like 1.1 millivolts. So essentially this one here is 0 volts. Okay, so 0 volts. So let's turn this, let's see, clockwise 90 degrees. So it's at the 3 o'clock position. And so now we see that the one that was a 0 volt, which is the one on the right, is now reading 3 volts. And the one on the left is at 4.2 millivolts, right? So now this is essentially the 0 volts. Okay, so let's keep going. This is now at position at 6 o'clock. And what do we get? Well, we get 3 volts for this side, for the right one, and we get 6 volts for the one on the right. Sorry, so it's 3 volts for the left, 6 volts for the right. Okay, we keep going. Now we're at 9 o'clock, and now we get 6 volts on the right and 3 volts on the left. And of course, you know, if we keep going, we end up back to where we started, which is 3 volts and 0 volts. And it just keeps going, you know? I mean, that is why this is just endless. So, so there you have it. We have proved that, you know, this matches indeed with what's on the data sheet. This information is going to be very useful for the next experiment where we're going to rewire this. We're going to bring in Arduino or write a little piece of code that will figure out when we're turning the knob either to the right or to the left, and then be able to do something with those values. Okay. Okay, for this next experiment, we have a very simple, actually the rest of the experiments, we have this very simple setup here. You can ignore this part. I'm actually getting power directly from USB, but we will be using one of the 5-pin 5 volts pins on the Arduino itself to provide power to our circuit. So the potentiometer, we're going to hook one of the resistive track pins, in my case pin 4, to 5 volts. Pin 2 is going to be going to ground, and then pins 1 and 3, which are the wipers, are going to be connected to the analog pin 0, which is 19 in my case, and analog pin 1. So if you're using a different Arduino, just make sure that it is an analog port, and just update your code to reference that, right? First, let's take a look at that relationship between the two. So I'm going to bring up the serial plotter, which you should be able to see right here on the screen now. And then notice what happens as I start to turn the pot. You'll see that the two values are giving me different information, right? But it's relative to each other. So it's not as apparent when I do this slowly, but look at what happens when I do this slightly faster. And I'm going to try to be consistent so you can see, right? So there you have it, right? You can see that the pattern looks very much like what we saw on that data sheet, right? Okay, so one other thing that you can kind of notice is you see these lines here, they're not 100% straight, right? There's a little bit of movement going on in there. There's some noise in there. So, and this is actually easier to see with the serial monitor. So as you can see here, I'm going to try to put this as close to 0. So as you can see, the values, even though 0 is seems to kind of be holding. Occasionally you see a different value jump up, but the other one, A0, it's like it's jumping between 498, 497. This noise, this jumping around, is also known as jitter. Okay, and so we're gonna have to account for that as well. Here we're looking at a port of Bjorn's code here. The logic is pretty much the same. I just made some changes here. The most notable and significant one is that I put this into a library. And this is actually a class now of Potentiometer, just so that I can, make it easier for me to reuse. The other thing, other changes I made, which is some minor changes just to make the code a little bit clearer for me. So let me walk through what's going on here, and then we'll take a look at one of these examples, which I've made here. So first off, let's take a look at the header file. So there's a couple of, I left quite a few of these variables public, so to make this a little bit more flexible. And things that are private, well, they're not really needed outside of the library, so we'll keep them private. All right, so if you guys remember, we're trying to identify the 4 different quadrants, right? Let me bring that page up again. So here, so we're basically going to be, we need to figure out a few things. We need to figure out the direction that each one of these lines are moving, right? And then once we know that, then we can figure out which one of these 4 quadrants we're on. So first, what we're going to do is, so we're going to be, sending this object here the current value of A and B that we're reading from A and B. In fact, if I go into my main here, I have defined pins A and B, and right here, I'm sending it the current value that the pin is reading, right, to this method here, update values, which is this one right here. And so what we're going to do is, first we're going to get the current value and save it as the previous value, and then we're going to assign the new value to the current value. And so then once we have these values updated, we can do all sorts of calculation with this. So the first thing we're going to do is, well, is the new value greater than the previous value? But remember, we talked also about this threshold. So, and this is to account for the jitter that we saw previously, right? So I have this threshold set by default as, I believe, 3. Yeah, 3. That should account for that single digit jitter that we were looking for, right? And so basically, if the difference between the two is greater, at least greater than that threshold for the jitter, then that means that if the new value is greater than the previous value, we're going it's going in this direction, right? It's going up. We're going from a low value to a high value, so that's up. If, however, the value is lower than the previous version minus the difference in that threshold, right? Then that means that we're going down, right? And then we're going to do the same thing for the other reading that we're getting from the other pin, right? And now that we have the direction, right? Now that we know whether it's traveling up or going back down on the cycle, then we can look into see which one of those quadrants we're on, right? So we know that if they're both going down, they are on the 3rd quadrant. If they're both going up, they're on that 1st quadrant, right? And then whatever they cross, if the cross happens while the values are on the upper half of the value range, then that's the 2nd quadrant. And if we're on the lower half of that value range, then we're on that fourth quadrant, right? And then let me bring this up again so we can see it, right? So those values are going up, that's the first quadrant. Both values going down, that's the second quadrant. And then when they intercept, if the values are on the upper range, that's the second quadrant. If the values are on the lower, they're on this fourth quadrant. Okay, so if we look at it over here, then we can see when both are going down, then we can evaluate, right? If value A is bigger than B, that means we're going clockwise. If otherwise, we're going the other direction. And then when the two values are going up, then if value A is less than value B, then that means that we're going clockwise. But otherwise, that means that we're going counterclockwise, right? And then for the ones where they intercept, if value A is greater than, right? And this is the tricky one. So value A has to be greater than that half point. Or value B also has to be greater than that half point. If any of those conditions are true, then we must be going clockwise. But if they're not, then that means we're going counterclockwise. And then, we're going to do the same thing, but we're going to, if value A and value B, if either one is lower than the half point range, then that means that we're going clockwise. But if that's not the case, that means we must be going counterclockwise. And then if we don't meet any of these conditions, then that must mean that we're not moving, right? Yeah, so what else I'm doing over here, just so that I can also use this outside of the internal logic here, I'm also recording whether we're moving or not. And this is going to be useful when we implement this right here, right? So then we can say, hey, if we are moving, right, then let's do all of this stuff. But if we're not moving, skip all this code, right? And yeah, so the rest of the stuff is just so that we can do some more interesting things with this. So let's take a look at the main.cpp here and see what's going on. So I have, I'm going to be printing 3 different values so I can show this, how this library kind of works. It's really, really, really simple. The first value is the value that the object itself is going to hold. Second value called local value, just I'm going to use the settings that I have configured for the object for the threshold and the range, etc. But I'm going to calculate a value that's local to the main scope, okay? And then for the alt value, we're actually going to do part of the logic outside of the library, okay? Does it compile? Yes. And so let's load it. Okay, let me bring up the serial console for this one. And so I have defined the default values as, the minimum value is minus 255 and the highest value to 255 from, for the object itself. But over here, I am setting a max value equal to 1023 and a min value of 0, right? Right here. And this is the one that's being evaluated outside of the object. So as we move the pod, you can see how the values are increasing, right? And they continue to increase until they get to their highest value. And then no matter how much we continue going in that direction, there's no more change. Now, if I start going the other direction, then we'll see the values decrease until they reach their lowest point, which in this case for value and local value are both the same, but for all value is just 0. Right? And this can be useful, right? Because if you just have a single value you're going to be controlling, then use the one from the object. But if you have multiple values you want to control with the same potentiometer, but they, and they have the same characteristics, say for example, you just want to update a MIDI CC, right, with the same knob, then just use another method to switch between the variables that you're updating, maybe another button or something. And then all you have to do is just, move your potentiometer and it will update whatever value you have it currently updating, right? Now, if you wanted to have more control, then you can also have the flexibility to do it like I've done over here outside of the scope of the object, the pot object itself. Okay, I'm gonna stop here. Before I end today's little session though, I wanted to also talk about why would we use one of these when we can use an encoder? Well, there's advantages and disadvantages to both of them. Potentiometers provide a continuous analog output, right? If you have a need to provide a very smooth, continuous response on your circuit, then a potentiometer makes more sense. The other thing is that potentiometers are simpler to wire. And as you can still see right now, we're connecting this potentiometer directly to the microcontroller. And this is because we're taking advantage of the fact that the microcontroller, the analog inputs have high impedance. So we don't even have to put any protection resistors like we did in the previous example, right? Now with encoders, you're going to be dealing with bouncing, whenever that switch triggers from high to low. And so in order to compensate for that, you probably want to put some capacitors in there to smooth that. On the other hand, if you need something where you're going to be dealing with just digital data processing, then maybe an encoder makes more sense. In conclusion, well, we took a look at this elusive device here, right? We attempted to make sense out of it, and I think overall we did. We explored the relationship between the two wipers, what kind of analog inputs we can receive from them. We also looked at the visual representation to try and understand how we could use that in code. And then we saw it in action in code. And then we briefly, of course, discuss, why would we want to use it and why not? So one thing is for sure, I know that I have now another tool available at my disposal whenever I need to think in terms of receiving physical input as part of my sketches, right? I am no longer limited to buttons or encoders or those potentiometers which are fixed. I have another tool in my belt. So yeah, there you have it. I hope that you found this informative. I know that I certainly learned a lot by researching it. And if you have any ideas of how you intend to use this or how you use it, I'd love to hear from them. So maybe share them in the comments. I encourage you guys to try some of these experiments and share them with everybody, and if you know something or you learn something, share it so that we can all benefit from this shared knowledge. If you like what you saw today, please hit the like button. And if you want to see more, consider subscribing to my channel. Until next time, bye.